In this video, I'm going to review Lorentz transformations in a way that assumes that you've seen these before in a modern physics class. And in particular, I want to relate how we're going to think about Lorentz transformations to how you might have seen them in a previous just upper division modern physics class. So Lorentz transformations, what they do for us is they allow us to calculate the space-time coordinates of events in different reference frames. Which is to say, if we know event A, which is maybe me snapping my fingers, we know event A occurred at some time and at this location in my office, in the reference frame of my office. And we know that, we're given that information. And then you're driving by in your car and you want to know where and when did I snap my fingers in the reference frame of your car. The Lorentz transformation allows us to calculate that. And then you could observe it and ask, does that match? And it would. It's important to note that these expressions didn't come from nowhere. And in fact, one can derive where they come from simply by enforcing the principles, the axioms of special relativity. So these just didn't come out of nowhere. They aren't just random equations. One can actually derive them from those two axioms, the principle of relativity and the fact that light moves at the same speed in all reference frames. So before I write them down for you, I want to remind you of a little bit of notation. So often we write these in terms of something known as the Lorentz factor. We usually use a gamma to represent our Lorentz factor. This is 1 divided by the square root of 1 minus v squared over c squared, where v is the relative speed of the two reference frames. So if one of the reference frames is me sitting in my office, the other reference frame is you driving by in your car, then it would just be the speed of your car. We often also write these things in terms of beta, which is just that relative speed v divided by the speed of light. Now, if you're working in units where the speed of light is 1, then v and beta are really the same thing. But beta comes up a lot. So it's really, beta is just the relative speed of the reference frames. So we can write our Lorentz factor also as 1 divided by the square root of 1 minus beta squared. It's just convention. It's just defining things here. So in your modern physics course, you probably learned some Lorentz transformations. And my guess is you learned a couple formulas that looked like this. T prime equals gamma t minus gamma beta x, or something that looks like that, depending on whether you were using gamma or beta. You know, if you plug in those expressions I have above, then this should look familiar. Or an x prime equals minus gamma beta t plus gamma x, and then y prime equals y, z prime equals z. So before we say anything else, these are Lorentz transformations for a particular set of reference frames. So these Lorentz transformations are for reference frame S prime moving in the x direction relative to frame S. Right, so this is specifically in the case where they're just the two reference frames are aligned such that one of them is moving in the x direction. You could write a similar equation for them moving in the y or the z direction, and it would just look like this. You just sort of trade out your variables. So often we just focus on that X direction. One way we could say this is that frame S is, or S prime, excuse me, is boosted in the X direction relative to S. When we talk about the word boost, or here I'm saying boosted, that's referring to moving between two reference frames that actually have a different speed. So there's some relative speed between these. We can talk about simpler reference frames. We could just rotate a reference frame, or we could translate through space. So I'm standing here and there's one reference frame, or maybe I'm at the origin and I'm looking at around me, or I can move over here and this is maybe a different origin, and so that's a translated reference frame. It's kind of boring comparing those two reference frames because things don't really change. It's just the numbers change, I suppose. Uh, Special relativity only really gets interesting when you consider boosting, which is to say, I'm comparing what I'm observing to what you're observing in some moving reference frame. Right, so that's why in your modern physics course, you really focused on these particular Lorentz transformations. And again, we focused on X because Y and Z really are it would work in exactly the same way. There's not a real difference between the Y direction versus the X because of this symmetry of the space that we live in. Okay, so you probably just wrote them this way. You did some algebra with these. You solved problems. Okay, that's all good. We could just do that, just like you did in your modern physics class. However, it is going to save us a lot of time, especially as the physics gets more complicated. Doing things this way would not be efficient. So instead, we're going to write our Lorentz transformations in matrix notation. We all have a fair amount of physics under our belts and a fair amount of math under our belts now. So hopefully we're all at least somewhat comfortable working with matrices. And we can use these to summarize our Lorentz transformations in a compact form. So in particular, for this Lorentz transformation, which represents a boost in the x direction, we can summarize those four equations in one matrix equation, which looks like this. This is again for a boost in X. And this matrix part of this equation, this 4x4 matrix, is referred to as the Lorentz transformation matrix. And this is a way of summarizing our equations. And right now you might be going, hey, that was actually more writing for me than writing just those four simple equations above. So at this point, it might just feel like we're making things complicated without any benefit. It might just seem like we're making things more mathematically complicated, and actually I even had to write more. And that might be true. But as the physics gets more complicated, doing things in this way is going to save us. And so when people really do special relativity beyond just the introduction special relativity in a modern physics class, what we are going to be doing is working with special relativity using this matrix notation. Again, the last thing I want to stress is this particular matrix is just for a boost in X. There are different matrices if you want to go to a rotated coordinate frame, or if you want to boost in a different direction, or maybe you're boosting in some direction that's a combination of the X and the Y direction. You can do all of those things, and they're just going to be different matrices that we use. And so we end up with a set of allowed matrices, which are going to be our allowed transformations in special relativity. Okay, so those are the Lorentz transformations, and in particular, those are the ones in matrix notation. Thanks.